My name is Dominik Charousset. I'm from the Hamburg University of Applied Sciences in Hamburg. And I'm here today to talk about two of my favorite things, C++11 and actors. And in particular, I'm talking about an actor library for C++11. And this library is just not possible in the old standard, as you will see later. And believe me, I have tried it. So I will start with a short introduction why we should focus on concurrency and distribution in the first place, and talk briefly about the problems we have today with implicit sharing, why it is not a good programming paradigm, and why we need to have better abstraction to build reliable applications. Then I will introduce the library itself, libcppa. Then I will talk a little bit about my implementation experiences with C++11, and then I will hand over to Matthias. He will talk about how he uses the library and how to build high-level distributed programming without sacrificing performance. So I think most of you have seen a slide like this, maybe 1,000 times over. It's the clock speed by the years. This is popular. This is basically old news. The article of Charousset is from 2005, and since then there was no change like we have 10 gigahertz chips or something. Multicores are here to stay, and we have to deal with it. And it is not only multicores. There are actually three trends we are facing. The first one is multicores. Since the early 2000s, we don't have any improvements in clock speed, but we will have more and more cores on end machines. The second trend is GPU programming, GPU programming to be exact, where you have a different kind of instruction set where you program with. And the third challenge is distribution. This is not just only cloud computing, but cloud computing pushed this a long way. So what are the tools we have in the standard? The three trends are parallelization, specialization, and distribution, of course. So what are the tools we have in the standard? We have mutexes and we have threads. This means when you are programming with these tools, you are responsible for the correctness of your program. You are programming classes, you are using your mutexes, and you have to make sure that all your mutexes are always in the correct order locked, that you don't have deadlocks or live locks or whatever. The thing is, you cannot test your program any longer if you are using threads and locks. If you are running your program for an hour, you can say, hey, my program can run 1 hour. If you are running it for a month, you can say it can run a month. But still, you have not proven your program to be deadlock free. And once you test it in a different environment, it might just deadlock. And to do multi-threading with locks right, you have basically to be an expert. You have to have a lot of experience. You will need years to do this right. And quite honest, once you became such a good programmer that you can do this right, you should do better things that are more valuable to your company than to solve the same problems over and over again. So the main problem with locks, I will illustrate with this short example. We have a class subject. This is a really simple abstraction over publish subscribe. You have a subscribe and you have a broadcast. And both member functions are guarded by a unique lock, which seems good at a first glance. And then we have another class that's called foobar. It's called foobar because it has two member functions, foo and bar. And those two member functions are also guarded by a unique lock from the class. But in the foo, we are actually calling the subject. We are calling subscribe. And it's pretty simple to have a deadlock in this with these two classes alone. So let's say we have two classes, two threads, a subject and a foobar in shared memory. So these objects are visible to both threads. And the first class subscribes a new functor to subject. This functor calls bar. And the second thread, meanwhile, is called broadcast, which means our functor is invoked while we are calling through from the other threads, and that's it. Your foobar calls subscribe, and the functor calls bar. The thing is, the designer of subject, or the developer that has written subject, could not know that anyone ever will pass a functor to its class that will call a bar that somehow calls subscribe. So the message here is mutable stateful objects are the new spaghetti code, which is not microed but from a chicky. And reason being is it is very hard to understand a log-based program, and libraries are no longer black boxes. You have to know what object uses which log, what function relies on what guarantees, how what functions are thread safe, and so on. So simply put, this is just the wrong level of abstraction to build applications, to build large applications in particular. But saying this is the wrong level, what is the right level of abstraction? So we want to have a programming model, a paradigm that we can just use, where we don't have to think of locks or race conditions or whatever. And this, when we compose large systems, we will end up someday, maybe we want to distribute some parts of our program. And if we are using direct functions calls and stuff like that, we cannot distribute our program unless we write code to distribute ourselves. So the interface of our components should be stable and not rely on things like stack and passing function pointers around. So we want to have interfaces between the components that don't care where the components live, that just are network transparent and parallel executable. So, talking about parallelism, I'm going to introduce the actor model, which is really simple, the actor model actually. There are 4 points. You use message passing instead of shared memory. You don't share state, because if you share state, you cannot distribute the application. And you can create new actors, and you have a failure semantic, meaning you can monitor other actors. And that's the actor model, basically. Sounds simple, but it has a lot of benefits. Like when we are using message passing and don't use logs, we can just program our applications, encode the messages that are passed, and don't care about any log, ever. And as I will show later, actors are very lightweight. You can have literally millions and billions of actors. And reason being is that unless like a thread, an actor doesn't need its own stack. So it is very lightweight. It's only have overhead of a few hundred bytes. And most of all, with the actor model, you can cover both concurrency and distribution in one model. So your code will be always the same, no matter if you run locally or distributed across a network. Yes?
And the message passing between the actors, when one actor passes a message to another actor, will it block if the other actor is still working on a different message, or is there like a message queue?
Yeah. So the question is, do actors block if you send a message? And no, they don't. They have a mailbox. This is basically a FIFO buffer, and I will show this later in detail. Yeah. why do we want to have a C++ library for actors, basically? And what we want to do with our library is we want to raise the level of abstraction of C++11 with an internal DSL. That means we want only use C++11 features. We don't want to have code generation. We don't want to have a language extension or something. We just want to have plain C++, so you can use it wherever you have a C++11 compiler. And we have very lightweight actors to ease concurrency. And we have actually a wrapper for OpenCL actors. So if you pass a message to an actor, you don't even know if this actor runs on a CPU or on a GPU, because you don't have to know. It's just you pass a message, you want the actor to do something useful, and you just don't care where it will run eventually. So to back up a little bit and to talk about challenges of hardware, of parallel hardware, we want to make use of parallel hardware, of course, because if we don't, our customers will not be happy. If we are using one core but they have 20, they will just buy another software. And to do this, we want to split our application into many tasks. And by task, I mean task. Don't think about threads. Just forget about threads. You want to split your application into as many tasks as possible without thinking about how this composition works at the end. You want to split your application logic into tasks. That's it. And you want to have small overhead to do this, because you will have hundreds and thousands of tasks. And you don't want to pay high costs to spawn such a task, because the task can run like 10 milliseconds. If you have overhead like 5 milliseconds to spawn it, it's just not worth it. So also support for specialized hardware, meaning GPU programming. You don't want to change your interface if you split some tasks that will run on the GPU, for example. And I will start us with a little example of matrix multiplication. This is the matrix class. It's basically a glorified wrapper around a vector of float. That's a little bit weird, but I will come to this later. And you can just use the apply operator to access with row and column to access an element, and with data you get the underlying vector. This is the simple matrix multiplication. It's a loop for the rows, a loop for the columns, and you do a dot product on each position of the matrix. The dot product itself internally is also a loop. So you're looking at basically 3 loops. And if you want to split this in tasks, you want to distribute the dot product internal. The smallest task you want to spread is the dot product computation. So if you are using C++11 standard library, then you will end up with a vector of futures. Then you call async, and at the end you wait until all your tasks are done and move the result. In libcppa, this looks a little bit shorter, but this is not how I would recommend to do this, but it fits on one slide. That's the main reason. Instead of async, you just call spawn. This will spawn a new actor, and at the end you wait until all your actors are done. That's basically it. And the third example is the OpenCL implementation. If you've never seen OpenCL before, just forget it. It's basically, by convention, the last parameter is the output parameter. So you have the left-hand and right-hand matrix as an array of floats. That's because OpenCL cannot handle 2-dimensional arrays. And that's the reason why matrix is a glorified wrapper around a vector of floats. And then you get the overall size of the matrix, the row and column you are going to compute, and then you just calculate the product, and that's it. And if you want to spawn an actor that will run on the GPU, you use spawn CL. because we have the source code as string, you have to pass the signature of the function as template parameter. This is this fvec. The signature is a vector of float goes out and 2 go in. As I've said, the convention is that the last parameter of the OpenCL implementation, this the result, is the output parameter, and we don't want to have weird things like that in our interface. So we just say this function will return a vector of float, and it will receive 2 vectors. And then we give it a source code, say the function name, which is kernel void multiply. So multiply is the function name. And then we give the dimensions for OpenCL, and that's it. Then you send it a message, like you would if this actor would not run on a GPU, and then you wait for the result, and that's it. Because yeah, in this example, you will have to actually send a message, because the GPU has a distinct memory. But as you can see, you're just using message passing and don't call the 20 or 30 lines of code you would have to call if you would do this with the OpenCL API. Yeah, so as you have seen, not much code. And we have run the code on a 12-core Linux machine with 1,000 times 1,000 matrix, so 1,000,000 tasks. If we are using the simple algorithm, which is 2 loops, we run about 10 seconds. If we use the actors, we will run in 2.4 seconds, which is not the perfect speed up. And if we are using OpenCL, 0.2 seconds, which is basically the time you need to ship the memory to the graphics card and back. So that's why we are using OpenCL, right? Yes.
So when you do all these sends to OpenCL,
it's 1 cent.
But in the outer loop, you do.
No.
Repeat the question.
Ah, sorry. The question is how many messages we send to the actor, basically. In case of OpenCL, we spawn 1 actor, and because the graphics card is inherently concurrent, we just send a matrix, and the OpenCL framework will run 1,000,000 lanes, run the algorithm 1,000,000 times in parallel if possible. So we just send a matrix to the basically graphics card, receive the result, and are done. So we ship the data only once to the graphics card. So what about async? Well, apparently you get an exception that says resource temporarily unavailable. Very helpful. As it turns out, you just cannot spawn 1,000,000 threads, at least in the default configuration of Linux. You can meddle around with Linux and say, I want to have whatever. But if you're just using Linux out of the box, you will, well, your program crashes, which is not helpful at all. Yeah, to summarize this short example, the performance is the performance of actors was not the perfect speedup. If you would expect to have a better runtime if you have a simple runtime of 10 seconds and you throw 12 cores on this. And you will have a better speedup if you just use 1,000 actors instead of 1,000,000, because if you're using 1,000,000 actors, you have more overhead, of course. Then you have parallel resources. If you have 12 machines, but you spawn 1,000,000 actors, that's not a very good fit. But the point is, it just runs, and you can have 1,000,000 actors in less than 2.4 seconds, which actually computes something useful with this time. So the actual overhead of spawning 1,000,000 actors is less than, I don't know. The difference is 1.2 seconds, so that's basically the difference. That's basically the overhead of spawning 1,000,000 actors, which is not much. So, long story short, threads don't scale well. Even if we could use 1,000,000 threads, this would not be very efficient because each thread has its own stack, which means on Linux, I guess I think they have something like 64K per stack, something like that. And even if you change the default to say 2K of a stack, which is very small, then you still have this 2K a million times, which is a lot of memory and will most likely consume all the memory of your host, which means that your program will drastically slow down because of swapping and whatnot. So I've shown you this little example with one send and receive in it. But what is an actor actually? An actor is basically an entity that is a function over its mailbox. Messages are received in a mailbox in FIFO order, and you basically apply a function to each message you are receiving in a loop, which means you receive a message and then you look into the message and see if it's a message for computing something, or is it a system message or whatever. You just have basically this message loop that the actor runs, and this looks like a switch case, and this is basically what we want to achieve in the actor library. What we don't want to do is a large if-else block where you look into some classes and do type ID gleich gleich blah blah blah, then do this. That's not what we want to do. We want to have a high-level abstraction that will abstract away most of the boilerplate code, actually all of the boilerplate code. So what we are using, if we are talking about a message, we are talking about a tuple. So you send tuples to actors, which means you can just say send actor 5 integers. Those 5 integers will be wrapped into a tuple and then sent to the actor's mailbox. And messages are buffered in FIFO order, and the handler for those messages is a partial function, which is a function that is not defined for all possible messages, because that's impossible. So you declare what messages your actor can understand, and I will show you how. This is running code, and this is, as you can see, lambdas all over the place. So that's the most important reason why you just need C++11 to compile this. We have a partial function that says if you receive a tuple with one element, and this element is a string that says hello, then reprint hello to the terminal. And the second pattern will react to atoms. This is atoms are short strings that are computed to integer constants. It's basically a hash function that is invertible. So you can annotate your tuples with informations. Because if you're sending 5 integers to an actor, this has no meaning. If you give me 5 values, I don't know what you mean. So you can just atoms to say addition or multiplication or whatever. So we can use these atoms to annotate meta informations, to annotate tuples with meta information. And because we want to repeat ourselves all over the time, you can say, I want to receive something that matches the signatures I'm giving you. So in this case, we want to receive 2 integers. So our lambda expression will have 2 arguments. And you don't want to say here on int, invoke this. And just say, if I receive something that matches the signature, go for it. And you can do, you can split your pattern basically. You can say if something comes in that has hello in the beginning, followed by a string, then use this callback. And that's basically it. As I've said, messages are tuples. So if you want to use parcel function by hand, you have to give it any tuple which wraps tuples of ordinary size of any type. Yes?
Did I miss the reason that you call this partial?
Why is it called partial? It is called partial because a normal function can be applied to everything you give it. And a partial function can only be applied to some values. So in this case, you cannot write a function that can handle all messages that are possible unless you do something like, for each message, do nothing. This would handle everything, but it's not useful. So that's why it's called partial function, because it's only defined for a subset of all tuples.
Thank you.
No problem. Yeah. To give a little example about actors, actually, as I've said, we have each actor has a message loop. But what you just do to set up this message loop is say become. This will set your behavior that you give to the behavior stack, and then you give a partial function with what you want to receive. In this case, we have a math server that offers a simple math service where you just send them plus with 2 integers, and it will calculate a plus b and send you the result. That's the message loop of this actor with 3 lines of code. And we have a client that sends a message to the server. So it says plus 40 and 2. And then means if you receive, you want to wait for the response. And if the response arrives, then it should look like this. And you do print 40 plus 2 is 24, hopefully. 42, sorry. But this is not. This is really not blocking. So if you're using sync send, then you send a message, and you change your behavior to match for the reply message. So if anyone else sends you a message with atom result and an integer, you won't process this message because it's not the response you are waiting for. Yes?
Is there a reason why you're not using static typing to enforce the rule that like the result is going to be of a particular format, and making all these partial ones?
Good question. The question is, why don't we use static typing? The answer is actors are, as you can see here, encoded by an actor pointer. So an actor is just an address, and you send it something. And we don't want to have the type information on the actor, because then you could not compose large systems. If each spawn operation, which you use to spawn an actor, would have the type encoded that it understands, then you cannot pass actor pointers around. You cannot make vectors of actors and stuff like that. In particular, it makes error handling very, very complicated, because each actor would have a different type. So you could not say for all vectors do something. It's basically a trade-off. We are trading, in this case, flexibility compared to type safety. But if you receive something that's different, so if the server would give you another message, right, then you would catch this in this actor, and you could write a handler to catch that, or you just would use the default behavior, which is shut down the actor and propagate the error to the whole system. Yes?
Wouldn't type erasure allow you to use, after the virtual call, you'd be able to match more exactly, not have to do runtime evaluation of as much?
The question is, why we not use virtual function dispatching with two tuples, right? And this is basically what we are doing here. So we have type erasure at the beginning. If you send a message, it will convert it to a tuple, and then you match for the actual type with this pattern matching.
But I was thinking even the actor using type erasure there, that it could match the tuples more directly.
Yeah. If you're doing this with pattern matching, you get a more flexible composition. And we don't, as you can see here, an actor is just, you can just use a function. You can use classes, but only if you choose to. So this is very little boilerplate code to spawn actors, because you can just use ordinary functions and don't have to implement an interface and overload virtual functions and whatnot. Yeah. So, as I've said, this become will set our behavior for the message loop. And if we use sync send, then we will set a handler that matches only the response. And if we have received the response, we will then return to the last behavior. So if you have, if you would send a message here, sync send, and after you have received the result, you would return to the outer loop, to the first become you set. Yeah, so this is the one-shot handler that matches only the response. And if you're using become, you set your your receive loop in motion. So you will basically loop forever until you decide to terminate the actor. And yeah, this actor doesn't set a become, so it just sends one message, sets a handler that matches only the response, and then it's done. And this is how you basically plug this together. You spawn a math server, give the reference to the math client, and yeah, wait until all actors are done. Yes?
Will it only respond to the response from that send, or will it respond to any response that matched the pattern?
Okay. The question was if this matches only the response to this particular message, and the answer is yes. This is why we are using sync send. You can use send and then use become to wait for a message that looks like this, but you have no guarantee then that this is actually the response you're waiting for. As far as network transparency is concerned, I will briefly show you how network transparency with actors works. So let's say we have two nodes, node A and B, and two actors, actor 1 and actor 2. And actor 1 wants to send a message to actor 2 that that runs on somewhere in the network. This dotted line is the abstraction. So everything that's beyond this line is not visible to the developer. So the first thing we have to do is to publish this actor 2 so that it's reachable by network. And this middleman is something that does all the serialization for us. So we don't have to care about where the other actor runs. Except we have to give a reference to the other actor. You call remote actor with port and host, and you get just an actor pointer that is not distinguishable, that you cannot distinguish from any other actor pointer you have. Maybe you spawn 10 actors and call remote actors, then this looks all the same for you. So the system creates a proxy for actor 2 and a middleman on this side. And if you are sending a message, then all the serialization is then transparently by the actor. And on the other side, the middleman will create a proxy for actor 1, which will be the sender of the message that is visible to actor 2. So if actor 2 calls reply, it would reply to the proxy, and you would go the other way, back. Yes?
Can the nodes be a different process of the same machine?
Yeah. Can the nodes be different processes? The answer is yes.
And what is your inter-process communication in that case? Can you use shared memory?
Do we share memory if the nodes run on the same host? Right now, no. Right now, it's always TCP, but it is something we want to do in the future because it's obviously more performant. So one of the great strengths of the actor model is actually fault tolerance. So what is fault tolerance in actor systems? So let's say we have two actors, Alice and Bob, and those actors are linked. That means they have a bound lifetime. So if Bob dies, Alice will receive a special message and vice versa. So actors can link their lifetime. Errors are propagated through so-called exit messages. And the default is if you receive an exit message that has a non-normal exit reason, you terminate your execution as well. So the idea behind this is you can build systems or subsystems where all your actors are either alive or have collectively failed. So you don't have weird states where your system is doing something. You are guaranteed that your system is either doing the right thing or shuts down completely. And you can trap those exit messages to handle those failures manually. And what you usually do is you have a hierarchical tree where you have actors that spawn workers, and all the workers are linked with each other and the server. And so if one worker fails, you can either respawn that particular worker or restart all workers, or whatever strategy is best for your problem. And in source code, it looks like this. We have the bob fun is the function that implements bob. All we know from this is it will fail for whatever exception or something. And Alice actually spawns bob with the linked option. So if you say spawn with nothing, then you just spawn an actor and don't care whatever when it dies or something. If you spawn linked, if you use this option, then you create the actor and make a link to it, so you will get a message if it fails. And then we send a message and receive something, but in this case, it doesn't matter because bob fails anyway. So yeah, you can use linked option, or you can use other options that use to achieve more advanced features. Self, in this case, always points to the actor itself. Like this, in an object-oriented environment, it just identifies the actor itself. So you can use self trap exit to receive exit messages manually. And yeah, and Carl spawns Alice, and this is how exit messages look like. It's always atom exit with the exit reason, and if the exit reason is normal, then your walker or whatever just finished execution. And if you have an error code like unhandled exception, you can treat this actor by rebooting parts of the system, or just propagate the error further. Yeah. Okay. A few facts about libcppa. It is an open source C++11 library. It will require a very recent compiler because we use a lot of C++11 features. This is the reason why we are currently not can run on Windows, because the Microsoft compiler doesn't support enough C++11 to get it running. But we support right now macOS and Linux with GCC 4.7 or greater or Clang 3.2 or greater. And feedback and contributions are always welcome. You can find our implementation on GitHub. It is released under LGPL2, so you can use it in commercial applications as well. And in our working group, what we are working on is actors on embedded systems, which is a hot topic for us because, say you have a network of sensor nodes, then those sensor nodes will have very limited hardware capabilities, but we still want to program with the actor model to have all the failure guarantees and the network transparency. And one thing that is in particular useful is you can test your application locally with all the actors that will run later in the distributed sensor node network, and you can distribute it then later after you have tested this on your machine. And another topic is actors in public subscribe, which means network layer multicast, which is again very useful in sensor networks, where you just plug your sensor nodes somewhere and you want them to configure themselves. And message routing and composability means that we want to extend the message passing by not sending a message to one actor, but to give the message a path through your actor system, where you can say, send a message to actor A and send the result to actor B that will then handle the result, and so on, until eventually you will receive the end result. before I conclude this talk, some things we are struggling with C++11 is, for once, we would very much like to be able to migrate actors at runtime, but it's not possible because you just cannot serialize a function. So you cannot serialize just the data in the function and resume the computation somewhere else, because you cannot serialize basically executable code. As you have seen, we use this match for messages. If you are familiar with languages like Erlang or Haskell, you are familiar with pattern matching. And if it's supported by the language, it gets way more powerful. And right now we are limited to any tuple because we need the runtime type information at runtime. And so our pattern matching is basically limited to this any tuple implementation. But we think that pattern matching itself has enough value to find its way to any language, basically. And the last point, of course, is that C++11 still has no serialization of data, which means that we have to write all the serialization abstraction. And if you want to send user-defined classes, you can do this, but you have to write little boilerplate code, which is very ugly and just should not be that way in the year 2013. Yeah, this concludes my half of the talk. Thank you very much. I will just hand over. One question?
Pardon me if I'm wrong, but it seems like a good percent of the code is taken up in string comparisons and string matching.
If you're, the question is, do we use a lot of string comparison? The answer is,
Seems slow, yeah.
the answer to that is, this is why we have introduced atoms, because you can compute integer values, like basically hashes, from short strings. So you can just annotate your messages with integer values that have a very that have a meaning, so you can add meta information to tuples without doing string comparison. And you don't have to copy strings all the time if you're sending atom values.
Do you have a reference to that specific part? Because I have a particular situation where the string matchings just take just a ton of them.
Okay. Sorry, the question was...
Well, I'll ask after.
Yeah, okay. Do it later offline.
Yeah.
Okay.
Do you have any plans for protobuf support and message passing part?
Yes, protobuf is on our to-do list because there is basically every web serving using it. And web support, like doing HTTP messages, is on our to-do list as well. But we just cannot use our messaging, which is a binary protocol, to talk to a web server. Yes?
Sometimes actors have what they communicate with is considered a report. Do you have an idea of a one-to-many or communication or fan out? Or is it a one-to-one on the send?
Do actors have ports? The answer is no. As soon as you have the address of an actor, which is an actor pointer, or if this actor is published, host and port, you can send a message to it. So you don't have to need you don't need a port to communicate to an actor. And we also have group support, which means you can you can actually spawn actors in groups if you want to address all actors at once after you have spawned them all. So you have one-to-one, basically end-to-end communication as well. So that's good. Does this work?
Good. Exactly 45 minutes. So in the second half of this talk, we'll look at how libcppa helps writing distributed systems. And in particular, we look at the network security main, which is my field expertise, and an application that I developed as part of my PhD research. So I begin with introducing this application and its domain, and then discuss general requirements that such applications exhibit, and finally show concrete examples about how to use libcppa in that domain. Okay, this network security, and specifically network forensics and incident response, is the case where we have an attack that occurs in a large organization, and you have to figure out what has happened. So the security analyst has to determine the scope and the impact. And what they do is they need to figure out, how did the attacker get into the system? How long did they stay under the radar until it had been detected? What was the damage for the organization, financially, in reputation, and in terms of data loss? And maybe also how we make sure that this is not going to happen in the future again. So the main challenge here is this data that we have to investigate in that context is by far much what you can analyze with current systems. These are petabytes of data that analysts have to go through, and they essentially find the needle in the haystack. And it dictates a distributed setup for processing such amounts. Another issue is typing. Often the data that the analyst has to go through is poorly typed. For example, consider the case where a machine has been hacked, and we want to know to which other machines the attack propagated. And often all we have is just an IP address to figure out how to go from one address to the other, but it's embedded in a log file, and text file, a string. And if there's no first-class support for IP addresses, it's very inefficient to perform address computations, which you technically could, because IP addresses support prefix matching and very domain-specific operations that are faster than just bulk strings. Finally, there's lots of heterogeneous formats that have to be investigated in such a breach. For example, packet traces are TCP dump files that are a completely different format than IDS logs or firewall logs. And really, it's important to streamline this process to save the costly analyst time. And that's part of my PhD, to build a system that facilitates this and makes it interactive and scalable. And on the right-hand side, you see a sketch of how the architecture of the system looks like. In the bottom, there's a persistence layer, which is kind of consists of an archive and an index. The archive has the raw compressed event data, and indexes are created to speed up the query of the data. And in the middle is a in-memory caching infrastructure. That's not only just to get the data in, but also to save intermediate results of queries. And it keeps fresh data accessible. So this is going to be a distributed system, and there's a recent trend in in-memory computation. So a large chunk of the actual data will reside in memory during the operation. And it's important to keep that up. And finally, there's analysts, intrusion detection systems, or other third-party applications that feed data into the system and get it out there. And you could imagine that intrusion detection system does both of this in a semi-automated fashion, where it queries for specific data, but also contributes logs to it. Okay, it is a distributed system. There's multiple machines involved, but the user interacts with it as a single unit. So let's abstract a little bit from here and hold that thought. How do we design distributed applications? So in general, we have components, and good software practice tells us that we split the tightly coupled parts into those pieces and leave a well-defined interface across components. And in distributed settings specifically, we have message passing along those lines. And our code that we write in distributed system ideally should be oblivious to the actual deployment scenario. So one machine can host that component, whereas the other just lodges these two. Important here is that since this is on one machine and maybe within one process, that we don't want to pay the price every time of serialization. So really, we only want to serialize if we are doing IPC or go to other nodes and want to rely on passing just the data around without serializing it across in each step. There's a safety issue that this data that's passed along must be const, or otherwise we have shared state, and I will go into more detail later. So what else besides flexible serialization do we want? We would like to have platform independence. In a cluster of commodity machines, we just want to add one box after the other and scale with the workload. Network transparencies, we've talked about that earlier. No distinction between local and remote. We don't want to litter our code with boilerplate that just handles those different cases. And we would like to have rich type messages, not just void blobs that we handle later, but also say coordinates or point, and encode those as messages. Finally, this point has been hammered home today many times. An asynchronous coding style is vital to achieve the performance. But today, we do this mostly with inversion of control by passing in callbacks. And that is non-local control flow that's very difficult to reason about for the programmer. And it is hard to do so and actually error prone. So very connected to that is a powerful concurrency model to harness multi-core systems without explicitly writing that boilerplate. So there is really today no real lightweight middle layer that we can leverage with a very high level of abstraction that uses these state-of-the-art C++11 primitives. And with libcppa, we're trying to really fill that gap and provide such an abstraction. Let's look at some concrete examples. I'm going now to show you how to do some of the stuff with the libcppa. And the first part I'm going to talk about is interfacing with third-party applications. So when you generally create a TCP server, what you do is you accept a TCP connection, poll a POSIX file descriptor, and if there's a new connection, you spawn it maybe in a separate thread, and you read from the data from the socket when it's available. And if thereon, the data that you've read then convert into an internal format. So that's, for example, a custom SSHD that feeds data into the system, sensitive security information where each log event constitutes a shell command that the user has entered into the system. And today we do this, as I just said, with an accept and then fork a new process that is just dedicated to that connection, or we use this thread. We can do this with ACO a little nicer without relying on spawning a new process on your thread, but then we have inversion of control. So here's a generic asynchronous IPv4 server implemented in libcppa. It is just basically a function that takes a port where to listen on an address, which is the interface, and a handler, which is an actor itself that receives the connection once it has been accepted. Then we spawn an acceptor, which is a helper class actually that exists within libcppa to handle, that performs the accept operation itself. It does it asynchronously, and as you can see here, this is a unique pointer, so that's a factory function that returns the acceptor. And then we enter a receive loop, which is an infinite loop that dequeues messages from the actor's inbox. And it does so in a blocking fashion, though. We haven't seen that construct before. That's both an asynchronous and, in that sense, I mean, non-blocking and a blocking API. So this is an example where you could use the blocking API. And our actor itself has replies to two different messages. The accept atom that kicks off the polling of the acceptor, And this is, by the way, this is a timed polling, so you just test whether there's activity on the file handle by the acceptor. And if you actually got an exception, not an exception, then you spawn a new connection. So this is a function that is templated, and you would give it a special connection class here that does the main work of reading and writing from the socket as the application requires it. And here you pass in a pair of read and write TCP stream extractions. And that connection that you spawn, then pass it as a argument in a tuple and send it to this handler, which was the argument of the function. And that's the entire code for it. And thereafter, when we've tried and accept, we just go back to the beginning. We send the last message that we've received, which is last equed, and send it to ourselves again. So we might just enter that loop again. If we receive the kill message because, say, the program decides we want to shut down, we're just going to invoke self-quit, and the actor terminates. So the key takeaway is not here really the implementation and the polling and all that, but the actual style of writing asynchronous applications. Okay, let's look at another aspect, agility through network transparency. On the right-hand side, what you see is a graph that shows 5 minutes of network traffic at one node of a 24/7 cluster of an intrusion detection system cluster that we use at UC Berkeley to monitor upstream internet connectivity. And it receives a slice of the traffic, a 27th of that traffic. And this intrusion detection system is also a data source for VAST, the system that I'm building. And on the x-axis, we see time, and this is chunk 5 minutes, and this is the data that's being in bytes, actually in megabytes, that's being sent. When we have a range of 5 to 35 megabytes per node, so that means up to a peak of gigabytes for the entire upstream network. So even within a short time window, we have a very high variance, and the distributed system we're building needs to scale with that workload and being able to buffer the peak. And for that, we need to provision accordingly at runtime. With these good workload distributions, we can either be under provisioned or over provisioned, and would like to, without process restarts, handle the current workload. That's what I call agility. And it ideally happens. I mean, and we can do this with libcppa without restarting a process, because we can cheaply instantiate a new actor, spawn it, and don't lose the in-memory state of our current system, which is vital because a large chunk of the data resides in the distributed cluster. Okay, here's an example of how you could wire those components at runtime. And the program is just an abstraction of the overall system that has a private member, which is a configuration, and a specific tracker that does some ID tracking. And what you check here is if the tracker actor runs on that machine, then we spawn it. We spawn it. It's a class-based actor. We give it the class and the parameter it needs to do its work. And we publish it to a specific port and to the host that's given by the configuration. If it's not the node that runs the tracker, we just say remote actor, and we connect to it otherwise. So really what we have here is just the actor pointer, and it's either existent on in that process, or it's a remote entity. So it's actually a very trivial example here that does not do this all fancy reactive analysis and spawns new actors based on the workload, but it shows the mechanism that's available to do so. And it's with this functionality, you can easily duplicate bottleneck components at runtime and shut down excess groups of workers, all that without process restarts. Okay, now we get at a more interesting topic where most of the systems have to prove themselves in order to sustain, which is composability. And in by modularizing code in basic object-oriented style of programming, we have techniques such as inheritance or composition. In libcppa, when we try to factor our code, we really think about factoring the behavior. That's a very functional aspect. The behavior is a function over the actor's inbox. And so for some of you who have a little bit more experience with functional languages, this seems very natural to do, but I'll still explain what it does. If we have two functions, partial functions, and these are, if you recall that from the previous talk, sequences of match expressions, and stop executing on the first match. So the order, really, of how that function is written matters. And we can use a construct, or else, that also exists in other languages, Scala or the STM monad in Haskell, to bring those two together. And it's essentially as if we would paste the two sequences of match expressions together. Now, a behavior that we've seen is a somewhat enriched partial function that can have a timeout. So if there's a timeout, if it fires, then the function will return without a result. So you can also compose it with a behavior, and we'll see why this is important later. You can also accept or promote essentially a composition of partial functions into a behavior. But you cannot go down again, because then you would have multiple timeouts, and how to compose those is non-trivial to reason about. Here's an example that I use in VAST to construct a mix-in that is the base class of an asynchronous source. And all derived classes from that essentially get that behavior, which the behavior itself here, oh yeah, okay, in this case I use an interface from libcppa that's class-based, so I derive from the event-based actor and override the init function. And in that init function, I tell it what it does. So first of all, this base class has a partial function, which I call running, and this is the running state of the actor. And when I match a event, I do some work with it, say ship it to another actor, serialize it, and index it, and so on. And I can also do this with for a vector of events. And I left out the actual state that's, that this actor keeps. So you can imagine there's further private members that it operates on. So that's why we use here a CRTP mix-in for the clients. Then what we do here is we specify the behavior. We become this partial function that's our own member, or else we take a behavior that's given in the client class. So here's an example. If we have a special source, say a file source that reads log records from the file, we would derive from this, and by contract we have to provide a behavior implementation, which is called by the base class to specify the specifics of the implementation. And that's the entire class. There's no more extra code except the manual work there. That's domain specific. Okay, now a very exciting topics that comes close to the limitations of C++. Let's get back to developing message protocols. And we can do this in an asynchronous style. And by asynchronous, I don't mean non-blocking, more the fire or forget style, where we have decoupled sends and receive. An actor A just sends a work order, sends another order. It's not really expecting a response. This enables loosely coupled systems, and libcppa's primitive to do so is the send function. Another way of passing messages is synchronous messaging, where you always expect a reply. We've seen that earlier as well, where we have essentially lockstep protocols. And when we start to compose those sync sends, we have a ping and expecting a pong, and send a stop message and get a done tuple back with a reply. We really would like to have a notion of expressing joint failure or how to compose those two functions. I'll give an example in a second. This primitive here that we have is sync send, but the composition of those sync sends is non-trivial. Other languages have done a little bit better at that, and they have a powerful primitive for composition. And Bartosz Chmielewski has been pushing this topic for quite a while, and he's done a great job at promoting it in the C++ community. And it is worthwhile embracing these concepts because they help us to chain stateful computations. That's essentially what a monad is. I'm not going to go into the details, just keep it very high level here. Every monad must implement a function which is called bind. Looks like a right shift equal. And think about it as a type trait. This is the type trait. This is the signature of the function bind here. This M is a monad, and it takes two arguments, a monadic A and a function that maps an A to a monadic B, and it returns an MB. And what this function does, it takes this function and applies it to this A. It strips away the context that it has, the enriched way. So think about some context, this monad, and it executes it on the A to produce a new monadic B. And only if that context is actually available. So what we would like to write to make our code pretty and to express this problem is something like that. It's a mixture of Haskell and C++, where we send to the this should have been B, sorry, it's a typo, where we send the actor B an atom ping, and when the response arrives, the pong arrives, then we want to start another sync send call. This is not the return from C++, it's the return from Haskell that wraps this operation into a monadic context. So it basically takes an A and makes an MA out of it. And then we want to continue only if that's successfully, and when we get a message done afterwards. So here we've sent the stop message. When that succeeded and when we get the done back, then we do something with the result I. So that is similar to what Haskell has implemented in the do notation. At the moment, we would have to write cascading style for that. So in libcppa, the way we would do this is we send the ping message, install a one-shot handler with then, and when we get the pong back, then we perform another sync send inside that handler. And then this goes deeper and deeper and deeper nested, and so our protocols that we develop, where each invocation depends on the previous one, gets quickly unreadable. And that's why it is helpful to have such powerful composition primitives as monads to really make this asynchronous coding style more readable. So in summary, what we've seen here is a first experience with libcppa, and I found personally that the offered abstractions really help to solve the domain-specific challenges. The coding style is asynchronous, it's local, the behavior is easy to reason about without having chains of callbacks and inversion of control. It helps to integrate with third-party APIs and offers a flexible deployment scenario for those highly dynamic cluster or cloud applications. The overhead is pretty low based on my initial profiling. I only see that 1 to 3% of CPU time is actually spent within libcppa. Where I see major work for future improvements is a concern that has been raised earlier here by Robert, how to really add typing information into this a runtime tuple information that we have. We don't really have statically at compile time. We can't check whether a response matches a request or whether behaviors are compatible and messages are handled at all. So there exist plans already to improve the debugging functionality and to make it easier to detect failures of unhandled message and such. So the parting thoughts that I want to leave you with is that this actor model is a very natural fit to modern distributed systems. it gains a lot of traction. There's other tools out there. libprocess, for example, which is used by a system called Mesos, a cluster scheduler system used by Airbnb and Twitter. Also, Anthony Williams has just recently pushed out its own actor implementation. Microsoft has its Casablanca, a similar styled or similar actor model approach restricted to the Microsoft community. So based on what we've seen so far, my wish list for the standard and the C++ community to respect would be to add more powerful concepts to the language that facilitate asynchronous programming. And it's not just small keywords or library changes, but we need to step out of our own domain and see how other languages have solved it successfully. And specifically, I would like to see first-class support for monads and pattern matching that would really help here.
So why do you have first-class support with monads, for monads as a library in C++?
So the question is, why can't we have first-class support for monads in a library? And if we go back to the slide, here is that there is no way in C++ to take out of this lambda, unstrip that value out of there and feed it into the next computation.
Well, I mean, so if you get rid of the infix notation and you just have a function called bind, right? The first function can be the monad of A, and the second function can be a function which takes in an A and returns a monad of B. So I
okay.
don't see where
so
we need a language extension for that.
It is, I'm not saying it's impossible to build a library-based approach. It is still difficult, though. You will run into some limitations. You will not be able to write the same style in a easily to reason about fashion. You would get the same semantics with a library approach, but it could be solved more generally, I think.
So what in particular are you talking about? Like having an infix bind operator?
So the question is, would already an infix bind operator help to do that? And
or like a do notation?
A do notation would really help, where we can avoid this nested cascading style that we currently have to rely on to achieve these semantics. There's another question.
Would it be helpful to implement a Zell domain-specific language with Proto for it, or have you thought about it?
I haven't thought of it. The question was if a domain-specific language with Proto in particular could be helpful here to do this. And I haven't thought about it, but it would definitely be a good starting point, yeah. We have seen also here yesterday a talk about exactly these primitives at compile time with the metamonad library. So extending these concepts to runtime would be really useful, because that's where the asynchrony of file I/O and network I/O would be a very natural fit.
How does this differ from Erlang?
Excuse me?
How does this differ from Erlang?
How does this differ from Erlang?
That also has the same sort of actors and...
It is essentially the actor model as presented in Erlang. Yeah. So libcppa provides, it brings the actor model from Erlang as it is known there to the realm of C++.
Okay.
But Erlang doesn't have synchronous messages, so you always do basically fire and forgot messaging and change your behavior, but you cannot guarantee that the answer you receive is actually the response. So that's something that goes beyond Erlang.
Okay, and second, you alluded to it earlier. How do you map M actors into scarce threads or processes? You can't.
So the question is, how do you create an N to M mapping between actors.
Right, or do you deal with that at all, or just let the underlying
So it's really up to you how to compose or how to connect those actors, how to send messages to them. You can use groups, for example, to hide a bunch of actors behind a single actor. Whenever you send an actor to that group, they will all be disseminated to the actors inside that group, for example.
So if you have one machine which has 8 core, you can configure your actual runtime to take advantage of the 8 core versus a 4 core single host.
Yeah. So the question is, if the machine has 8 cores available, if I get
another one which has 4.
Another one which has 4 cores, how do we
adjust? Right.
Adjust, yeah, that without really changing the application.
By default, the actors are scheduled in an internal thread pool that is by default has many threads as you have cores, but you can change this if you want to have more workers or less workers. You can do
Any other questions? Yeah.
So have you considered that as the actors become more complex with what they're trying to do? If you go back a couple slides, it's starting to become fairly complex. That perhaps instead of
The slide or the implementation, the code.
forward a couple. Right there.
Okay. So the question was.
So as it's becoming more complex, and you're trying to cascade what's going to occur on these asynchronous or synchronous events, perhaps something else makes more sense, like maybe a state machine or some other type of. There's lots of other technologies that work well with messaging and what to do on the next event that are much easier to reason about than cascading anything.
That's a very good question. So the question is, there's other constructs that we know that are easier to reason about than cascading send response pairs such as state machines. And correct me if I'm wrong, Dominik, but I think there is actually plans to add those to libcppa, specifically state machine-based actors.
On one side, we have that, but if you don't rely on this matching of the actual response message, you can just do multiple behaviors in your class. For example, you can have multiple members that are behaviors, and then switch with become to the next behavior, like you would do in transactional state machines. So the sync send is really the point of the sync send is if you have if you have to have the guarantee that the response is really from the actor you have sent the message, then you can use sync send. Otherwise, you can just use SDM techniques, not SDM. Yeah, sorry. Do you want to conclude your talk?
Oh, yeah, actually, I think I have another slide. I forgot. Probably. Wait. Oh, that was it. So, really, we're really at the end here. And yeah, check out the GitHub project page and try it out. It's still in a phase where feedback would be really supported, just because the C++11 compiler support, and in combination with the systems and libraries, is not at a phase where it's just totally works out of the box on every platform. So any feedback is appreciated. We also have an IRC channel where you can just chat with us interactively. Thank you for your attention.